we have the slope of a line. If you've got a line in the xy plane and your points, we're going to label them x1, y1 for the first point and x2, y2 for the second point, then you can calculate the slope of that line using any 2 points along the line like this. And we're going to use lowercase m to be the slope. So you might have a question on your test. You definitely have a question on your homework that says, exercise 2, find the slope of the line passing through these 2 points. This is just applying the formula. You can label this point 1 and this point 2, or you can label this one point 2 and this one point 1. It does not matter how you label the points. You will get the right answer either way. But let's go ahead and label this one x1, y1 and this one x2, y2. And then my formula becomes y2 minus y1 divided by x2 minus x1. So negative 1 minus 4 is negative 5, and 1 minus negative 3 is 4. My slope is negative 5 over 4. And anytime I specify 2 points in the xy plane, that completely and uniquely defines a line. Right? Imagine like lining up your ruler or your straight edge against 2 points that you see. There's only one line that goes through those 2 points. And that has slope negative 5 over 4. So the next thing is called the point slope formula for a line. It says if you want a line in the xy plane that has a particular slope m, and it passes through a given point, we'll call it x1, y1, then this is the formula. It's saying the difference in the y values away from that original point is equal to the slope times the difference in the x values away from that original first point. So exercise 4 might say write the point slope formula of the line passing through these 2 points. And the first thing you would do is find the slope. And we already found the slope. It was negative 5 over 4. And then the second thing you would do is you would apply this little formula here and say, well, okay, what about y minus 4 equals negative 5 over 4 times x minus negative 3. And then you could do this if you want to simplify, because x minus negative 3 is the same thing as x plus 3. Are there any questions so far? No? Okay. So maybe you've seen this before, but also maybe it's been a little bit. And so you have to take a moment to memorize this, because this will be important if you don't have this memorized already. Okay. This is called the slope-intercept formula for a line, where m is the slope, again, just like it always has been, and the y-intercept is the place where the line passes through the y-axis, and the coordinates of the y-intercept are always 0 for the x-coordinate, and this time lowercase b for the y-coordinate, and that's what we're talking about here in this formula when I say plus b. Y equals mx plus b. That's going to give me a line with that y-intercept. And so now, if I ask you, write the slope-intercept formula of the line passing through these 2 points, number 1, find the slope, like we did earlier. And we found the slope to be m equals negative 5 over 4. And number 2, step number 2, you're going to first find the point slope formula. And a minute ago, we decided the point slope formula was y minus 4 equals negative 5 over 4 times x plus 3. And then the third step, after we found the slope and we found the point slope formula, is we just have to rearrange it to look like this formula. Use your algebra skills to rearrange this thing. And so what I mean is distribute the negative 5 over 4. So you get negative 5 over 4x plus negative 5 times 3 is going to be negative 15 over 4. And then add 4 to both sides. And adding 4 to both sides is the same thing as adding 16/4 to both sides. So that's going to be 1 over 4. And there we go. I can tell that my slope is negative 5 over 4, and my y-intercept of this line is going to be 1/4. Okay, so we haven't done any calculus yet. This is a review to kind of scaffold what we're going to do next. Y'all are comfortable with this? Okay, let me know if you have any questions. Now here is the calculus part. For a given curve, where I set y equal to some function of x, so we're talking about a curve in the xy plane, its tangent line at a certain point where the x-coordinate is equal to some x0, the tangent line is the line that touches the curve at this point and where the slope of the line is the derivative evaluated at that point. So let me show you what the tangent line looks like, because you'll probably recognize it right away. But that's an important definition. On Desmos, try this. Type in something like that, just a function, f of x equals whatever you want. And then type in something like this. And what that's going to give me is a point where I can slide it left to right in Desmos, because the x0 is just a constant that I can arbitrarily pick. And the y-coordinate is fixed, though. It has to obey whatever function I gave it, because I made the y-coordinate f of x0. Does that make sense? So what I'm going to do next is I'm going to use the point slope formula for a line here. Whenever I type y minus f of x0 equals f prime of x0 times x minus x0. And does everybody see why this is the point slope formula for a line? Because it would be like y minus y1 equals m times x minus x1. Except the y1 is going to be the y-coordinate of this coordinate pair that I put in, which is f of x0, so y minus y1. On the right side of the equation, m is going to be the slope. I want the slope of my tangent line to be the same as the derivative of the function. And then x0 is the x-coordinate of my point that I want on my line. And so now, with this setup in Desmos, I can grab the point where the line intersects the curve, and I can scooch it around, and you can see what all of the tangent lines of this function look like. This is a really big dot. I want to make it a little bit smaller. Something like that. Okay. For the most part, it seems like most tangent lines are a line where it intersects the curve, but it doesn't actually pass through the curve. Like if you zoom in into a small neighborhood, there's only one point where this line touches the curve and it doesn't actually pass through it. It stays on the same side of the curve. And that's almost always true. I say it's almost always true because like if I make x equals 0 here, that is a tangent line that actually does pass through the curve at the point x equals 0. So sometimes the tangent line passes through the curve, but for the most part it doesn't. And like I said, the important part about this line is that the slope of the tangent line is the same thing as the derivative of the curve, and so the slope of the tangent line matches the slope of the curve. Like when you zoom in close enough, the curve looks like a line, and the line that the curve looks like is the tangent line. That's the main idea. So this is important for calculus, and it's important for math in general, because the more you study math, I mean, if you want to become like an engineer, mathematician, whatever, if you want to be a highly technical person, the more you study math, you'll recognize that it branches off in kind of two directions. There's part of math which is dealing with lines and linear things, lines and planes and other generalized linear functions of multiple variables, right? And you learn how to solve those, and you learn how to solve those in the most efficient way, and there's a whole field of applied math where it's just about calculating with linear objects. And then there's another side of math, kind of like left and right lungs of the same thing, where you study the nonlinear parts, you know, the stuff that has curvature in it. You study multivariable functions and other objects in math that have nonlinear aspects to it, kind of like this red curve. And the trick is you never solve those problems directly. You always end up at the very end of your thing rephrasing the question so that your nonlinear math objects look linear. You make a linear approximation to the nonlinear thing. And then you use the techniques that you learn from the linear side of math to actually solve the problem. And if you need to, you iterate this process over and over again. But the big idea behind this, behind like all of what we know in applied math today, is that if I take any nonlinear function, and if it's an analytic function or a natural function like this nice sine curve, then if I zoom in close enough, it should look linear. So linear approximations are okay within a certain neighborhood of where I'm working. And then if I have to shift that neighborhood over time, that's fine too. But for Calculus 1, for our class, we're going to use the tangent line as this idea of like a good linear function. So it's a super duper simple function that actually approximates my big complicated nonlinear function within a particular neighborhood of a point. So anyways, today we are finding tangent lines, but that's the big picture of like why is this important at all. And the cool thing about this Desmos setup, if you try this at home, is now you can change this function to be whatever you want. If you want your function to just be x squared. Now I can still take the point and drag it around and see what the tangent lines of this parabola look like. And so on. Here's the cube root function. And one thing that's a little bit interesting about the cube root function is that at x equals 0, the tangent line would be a vertical line. And so it's going to not show up on Desmos as a vertical line because it'll say that the derivative is undefined here. But sometimes your tangent line can be vertical. Let's see. So how do we do this without Desmos? Like exercise 9 says, find the slope-intercept formula for the line tangent to y equals x squared at the point x equals 2. So my slope-intercept formula is something like y minus y1 equals m times x minus x1. Now, the x1 point is where I want my tangent line to intersect my function curve. And my y1 is going to be what does it look like when I actually use my function to evaluate where is the y value when x is equal to 2. And so that would be like 2 squared in this case. So we'll say y1 is 4. And then the m part, the slope of my tangent line, should be the derivative of this function, evaluated at the point x equals 2. And so what is the derivative of this function? What's the derivative of x squared?
2x.
Yeah, the derivative is going to be 2x. And so whenever I have m, that's going to be 2 times 2. So the derivative is going to be 4. And now I can use this formula, and I can actually write my answer. Y minus 4 equals 4 times x minus 2. Just kidding, that's not my answer, because my answer is supposed to be in slope-intercept form. So we're almost there, but we have to do like you did back in algebra. You have to still simplify this a little bit by distributing the 4 and then adding 4 to both sides. And that's your answer. And this is like the new skill for today, right? It's not a very heavy day. But do you guys have any questions at all about how he did that? Do you understand how he found y1, how he found the slope, how he put it together?
Could you go over how you found the slope again?
Yeah. Okay. So to find the slope of my tangent line, remember the slope of the tangent line should be the derivative of the function at the point. And so we took my function, took the derivative, and then we plugged in x equals 2, because that's where we want my tangent line to intersect. And then that's how we found the slope. Yeah.
Okay.
If you remember anything from today, the slope of the tangent line is the derivative of the function at that point, at the point where it intersects.
Will we always be given like x1 or y1?
Yeah. Yeah, I will always give you the x coordinate for where I want the tangent line to intersect the curve. Yeah. Okay, let's do another example. Just below it, this says, find the slope-intercept formula for the line tangent to y equals sine of x at the point x equals pi. So, my original function that I'm given here is sine of x. The point here where I want my curve to intersect is pi. To get the y value, you are just going to plug in the x value into your function. So what is sine of pi?
Really small. 0.05480366.
So this is a great learning opportunity, but you just used the degrees in your calculator. You know how your calculator can be set to radians or degrees? If I give you pi as an angle, that's a clue to use radians, not degrees. If I want you to use degrees, then the angle will be something like 30 or 45 or 60 or 90. But if I want you to use radians, it'll look like pi or pi halves or pi fourths or pi thirds or something like that. So using radians, what is sine of pi? 0. Yeah, and you don't even really need to use your calculator if you've memorized that nice unit circle. Because pi is a part of the unit circle there. Now, we figured out x1, y1. We also need the slope. And to find the slope, I need the derivative, because the slope of my tangent line is the derivative of the function. What's the derivative of sine? Cosine. And what is cosine of pi? It's what? It's -1. Okay, so now that I have everything I need, I just write down my point slope formula. I subtract 0 and multiply by -1, and then it's x minus pi. And to simplify, I distribute the -1. And there it is. That's my slope-intercept formula for the line tangent to y equals sine of x at the point x equals pi. So you'll definitely get one of these questions on your upcoming test. And when you do, you hope that by that time you've practiced with the homework exercises. As you're doing the homework, if you want to check your answer to the homework, like did I get this tangent line correctly, the best way to do that is Desmos. Desmos is very easy for checking tangent lines. I have my original function y equals sine of x. And then I just type in the tangent line I found. And you should be able to just visually confirm that that's a tangent line. There's not a lot you have to do. You can tell that it intersects at the point where x is equal to pi and y is equal to 0. There's some round off error going on here. That's why it's not exactly 0, but it should be exactly 0, right? Because calculators have to round numbers. And so that looks right. Are there any questions about how we did this one? Super simple? Okay. Find the slope-intercept formula for the line tangent to y equals x cubed at the point x equals 0. Okay, so once again, the function that I'm given is x cubed. The point that I'm given is where x is equal to 0. So I need to calculate the y coordinate. And to find the y coordinate, I just plug this into my function. It's going to be 0 cubed. And so the y coordinate is going to be 0. To find the slope is going to be the derivative evaluated at the point that I'm given. So it'll be the derivative of 0 this time. What is the derivative of x cubed? 3x squared. And so if I want to evaluate this derivative at 0, that's going to be 3 times 0 squared. And so my slope is 0. Let's use my point slope form. So memorize y minus y1 equals m times x minus x1. And then y1 is 0, m is 0, x1 is 0. Kind of a weird formula, but when I distribute the 0, I just get y equals 0. And that is not the right answer. I kind of briefly showed this to you on Desmos. You know, it was really fast, so maybe you missed it. But if I've got the, oh, sorry, that is the right answer. I'm sorry, I was thinking about something else. I'll tell you what I was thinking about here in a minute. No, we did find the right answer. So we did everything correctly. This is correct. That's the slope-intercept formula for the line tangent to y equals x cubed at the point x equals 0. And you can see it. If I type in y equals x cubed and y equals 0, that's clearly the tangent line, because the function goes flat there. No, so what I was thinking about just a moment ago when I said that was the wrong answer, what I was actually thinking about is this. Let me show this one to you. Because right here, if I had the cube root function, then the tangent line at x equals 0 is actually vertical. So the tangent line for this would be the line x equals 0. It doesn't really have a slope-intercept form. In fact, I don't have it in my notes, but let's try that. Let's try to find the tangent line for the cube root of x and see what we get. I wonder if the math works, you know? Like if the same process can be found used to find the tangent line of cube root of x this time. So the original function I'm given is x cube root, sorry, I miswrote it. The 3 should be right here. The cube root is the same thing as x raised to what power? 1/3. And when I take the derivative, what's the derivative of x to the 1/3 power?
1/3 x, negative 2/3.
Perfect. 1/3 times x to the negative 2/3. That's just the derivative power rule. Okay, and now I care about when x is equal to 0. So to get my y coordinate, this is going to be 0 raised to the 1/3 power. And 0 raised to the 1/3 power is what? 0. And to get my slope, I need to evaluate the derivative where x is equal to 0. So that's going to be 1/3 times 0 to the power negative 2/3. What is 0 raised to the power negative 2/3? 0. And 1/3 times 0 is 0, so my slope is 0. Let's use my formula now and see what we get. Because I think this is going to give me the wrong answer. Oh, okay. I see what's going on. I can see a few seconds into the future. Let's think about this again. When I have 0 raised to the negative 2/3 power, or really, let's back up 1 minute farther and we'll look at this instead. When I have x raised to the negative 2/3 power, do you remember that the negative is the same thing as the reciprocal? Like a negative exponent tells me to take the reciprocal. So x to the negative 2/3 power is the same thing as 1 divided by x to the 2/3 power. Okay? Negative exponent tells you to take the reciprocal. Now, if I write it like that, it becomes more obvious what the problem is. Now we can understand what's happening. We say the slope is going to be 1/3 times 1 divided by 0 to the power 2/3. Okay? And so now, what is 0 to the power 2/3? 0. Okay. So at this point, we say, I cannot divide by 0. Dividing by 0 is an undefined operation. So our slope is undefined. And if I was trying to use this formula, then it would look like this. I just can't do it. Okay, so that explains my confusion about the whole x cubed thing. If you take the tangent line of x cubed at x equals 0, it really is the flat line y equals 0. If you wanted the tangent line of cube root of x at x equals 0, you're not actually going to be able to find it using this method. And the problem is that the slope is undefined. When you actually go to the graph and you ask yourself, why is the slope undefined? It's because the tangent line is vertical. What's the slope of a vertical line? You know, what's rise over run when your line is vertical? You're dividing by 0. So, questions about that? Does that make sense? Okay. A function is differentiable. This is a vocab word that you should be familiar with. We'll use it a little bit this semester, the word differentiable. A function is differentiable if the derivative exists. Differentiable just means you're able to take the derivative. If we take any differentiable function and you zoom in really close on Desmos, it will look like a line. I don't know if I showed this to you yet, but there are some functions that are not differentiable. Let's take the function y equals absolute value of x. If I were to zoom in on this function, and I guess I should keep the grid so that you can see how far we're zooming in. If I just continually zoom in on this function, it never, ever, 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 ever starts to look like a line. It always keeps its V shape. So this function is not differentiable at the point x equals 0 here. But most functions are. You know, just pick any weird function you want, like the arctangent function. And even though it might seem like an odd function, the inverse of the tangent function, you zoom in far enough anywhere on this curve, and it looks like a line. You know, make up a really silly function. And it's differentiable. You zoom in close enough, and it looks like a line. That's always true for most functions. I guess I shouldn't say it's always true. It's true for most functions that we deal with. Most functions that we're going to care about are differentiable. And the tangent line is a good approximation of the function within a small neighborhood of the point of tangency. So the point of tangency is the point where the tangent line intersects. And that's it. I really intended for today to be a really light day where we don't learn a whole lot of new stuff because we know we have a test coming up and I don't want to like hit you with a lot of new material when a test is coming up. We already have learned a lot of new material. Again, look over all 5 homeworks sheets that you've gotten so far and make sure you're really familiar with that before Thursday or Friday, maybe. We'll see. But make sure you've memorized your derivatives. That's going to be tested for sure. Make sure that you have figured out how to use the derivative product rule. Make sure you figured out how to use the derivative quotient rule. Make sure you've practiced a lot how to use the derivative chain rule. That's very important. Remember, taking a second derivative is just taking the derivative twice, So you have to be really careful not to make any mistakes because it's just extra steps, right? If I ask you to take like the 50th derivative or the 2000th derivative, chances are there's going to be a pattern that you can recognize that shows up. So you don't actually have to take 2000 derivatives by hand. You can just recognize what the pattern is and try to extend the pattern. And then now you know how to do tangent lines. An inverse function is one such that when I compose the inverse function with the original function, I just get this back. I just get plain old x. And one example that we gave is like if my original function is x cubed, then my inverse function would be the cube root. And that's because if I were to take the cube root of x cubed, in other words, if I were to compose the inverse function with the original function, I just get x. And these come in pairs. Because if my original function is the cube root of x, then my inverse function has to be what? The cube root of x is x to the 1/3 power. The cube root of x and x to the 1/3 power are exactly the same function. If I want the inverse function, it would be x cubed. And this is because if I had the cube root of x composed with x cubed, that just gives me x. And this is the definition of what it means to be an inverse function. So you learn this in college algebra, and it's totally fine if you've forgotten it, you know. Everybody forgets things, and it's been a whole year probably since you saw this last, so, or more. I know there's some students that, you know, you take pre-cal, and then you take a 2-year break or something, and then you go to calculus. That's tough. It's very tough to catch up and remember everything. So I feel for you there. But this is the definition of the inverse function. This is something that we should know. Hopefully we remember this. And so, you know, if the function f is inverse to g, then g is inverse to f. It goes both ways. It's like my brother. My brother's name is Jeff. I'm Jeff's brother, but it also means he is my brother. It's a two-way street. And so an equivalent definition that I could have written is I could have said that a function is an inverse function if I compose it this way. And I always get x, right? It doesn't matter the order of the composition for inverse functions. Ordinarily, function composition does matter. The order of it does matter. But in the case of inverse functions, you always just get back x. Let me give you another little example too. If I have this function, I think that the inverse function would be this. Let's check. Let's check to see if I'm right. Because all I have to do is compose it. And composing this means I take my original function and plug in the inverse function here. So where the x is, I'm going to put f inverse of x. where the x exists in my original function, I'm going to plug in the inverse function. All right, so instead of x plus 2, I've got the whole inverse function plus 2. And then down below, I've got 3 times x minus 1. No, not minus 1. Sorry, I was looking at the wrong thing. That should be plus 4. Okay, so I just looked at my original function, and instead of having an x, I'm plugging in the whole inverse function for the x. All right, so ideally, since these should be inverse functions, at least I'm trying to make them inverse functions, I should be able to just compose these two and get x back. This does not look like x, does it? But we can try to simplify a little bit and see what happens. Simplifying is sometimes easier said than done. Let's talk about this. In the numerator, let me multiply both of these terms. Actually, heck, let me multiply both the numerator and the denominator by 3x minus 1. And you know, multiplying by 3x minus 1 divided by 3x minus 1, that's like 5 divided by 5. What's 5 divided by 5? 1. So it's like multiplying by 1. I'm not changing the value of this thing. I'm just using this as a trick to simplify. So when I do negative 4x plus 2 divided by 3x plus 1 times 3x minus 1, then it's just going to be negative 4x plus 2. And then the 2 times 3x minus 1 is going to be 2 times 3x plus 2 times negative 1. So that's my numerator. In the denominator, I've got, let's distribute the 3 to get negative 12x plus 6 after I distribute that 3 inside the parentheses. And then this 3x minus 1 cancels that 3x minus 1. And then I'm going to distribute the 4 so that I get 4 times 3 is 12x minus 4. And then now, negative 4x plus 6x is 2x, and then the 2's cancel in the numerator. In the denominator, negative 12x plus 12x cancels, and I get 0. 6 minus 4 is 2, and so 2x divided by 2 is x. So I was right. I guessed correctly, because whenever I compose these functions and I simplify, I should always just get x.